Hello, everyone. My name is Khalil Estell, and welcome to my talk. We'll be talking about how to reduce your binary sizes for embedded systems using C++ exceptions. Let's get started. So before we get started, I kind of want to talk about a little bit about myself, give you a bit of my background. I graduated from San Jose State University in 2017, and I'm an ex-Googler. I worked there for about 6 years before I quit back in January. If you want to talk about that, we can go to the pub and have a big old long conversation. Some of the products that I worked on, I need to confirm that my cursor works. Let me do that. L, come on. There we go. Nice laser pointer. All right, so I worked on the first Google Pixel Watch. I was the DRI, or the directly responsible individual, for the bootloader, the speaker, the microphone, and the haptics, not exactly by choice. And then also, when it comes to the Pixel Buds, which is kind of hard to see with this white background, I was one of the low-level system developers for it. And one of my main areas of expertise, or area that I worked on, was trying to get the code size as small as possible so we could fit more features and also fit in bug fixes and whatever else we might need. I'm also a volunteer at San Jose State University. I've been doing that for about 7 to 8 years. I've been teaching courses, and I'm also the sponsor and mentor for the San Jose State robotics team. Before we go any further, I want to tell you guys about the motivation about why this talk exists and why I'm here. So, like I said, I was a teacher. I taught a class called Computer Engineering 146. It is the Intro to Embedded Systems and Real-Time Operating Systems. And in this class, I gave my students a software development kit called ACCU Dev 2. It was written in C++. And I tried my best to stick with the C++ core guidelines as strongly as possible. And here's just a picture of the development board that I made for my students so that they could do the class. Now, one of the things that I teach my students is about the constraints of embedded systems. It's not like working with software that's on an operating system or on your laptop. We're limited in storage and memory. Typically, our devices have small amounts of read-only memory and small amounts of RAM, so about 8K to 32, but that's not exhaustive. You could have devices with way more RAM and way more flash, and then 8K to maybe 5 kilobytes for the SRAM size. A couple of examples. A very common device is called the STM32F103, which has about 64 kilobytes of flash, containing all your strings, read-only memory, text, code, and about 20 kilobytes of SRAM. The LPC4078, which is actually featured on that board that I made, one of my favorite chips as well, has 512 kilobytes of flash and about 96 kilobytes of SRAM. We don't have such things as OS-level constructs. You can't open a file. There's no idea of a file on your embedded system. There's no time. There's no network. None of that. You can create these using hardware that you have available to yourself, but these aren't available by default. You either have to write these yourself or find a library that supports this for your particular target architecture. So with so little memory, how do you prevent running out of memory or memory fragmentation? And the answer to that is that you just don't dynamically allocate. You just omit that from your entire code base. So there's no new, there's no delete. There's also no free, malloc, realloc, calloc. None of those things exist. Well, because those things don't exist, we also don't have string, vector, unique pointer, unordered map, shared pointer, none of those things. Anything that allocates, we omit from our code. But if you did want some of these things, you could use the ETL, the embedded template library. This provides you a lot of the containers that you would normally need, except you statically bound their size. So this all kind of comes together to explain why embedded developers stay away from C++ exceptions. Number one, and these are things that I've heard around the grapevine, people say that it requires dynamic memory allocation. This is a requirement, can't get away from that. It also requires additional ROM. It brings in the entire standard library. I've had some students and some other people tell me this, like, yeah, you have to bring in the entire standard library to even throw something. You need runtime type information for the system to be able to identify the type thrown to the type caught. The exception tables take a lot of memory. The exception algorithms take up a lot of memory. And on top of all of this, it's non-deterministic in propagation time, and the propagation is slow. So here's the thing, even though you don't know what the time is, when you get the answer, it's gonna be awful. So, back to class. Let's go back to class for a sec. So in this SDK that I developed for my students, I built a set of interfaces for my students to build upon. I gave them the interface and said, hey, implement these interfaces. One of such interfaces was output pin. Output pin, this is a very basic, slideware type version of it. Only has a couple of functions. And one of the things that I was considering, and actually before I go any further, let's explain what an output pin is. When you have a microcontroller, you have little pins that come out of the device. You can set the voltage of those pins from low to high, to a low voltage to a high voltage. And you can use that little function driver level, P high, to set one of those states. One of the things that I was considering was, is returning void acceptable? And I was like, well, what would I return? I don't need to return anything. I'm not getting any information. So maybe I want to return a status or an int or a bool. And I wasn't sure until I started thinking about other cases where this thing could be used. We're going to make a slight detour over to I²C. So I'm going to go over a very simplified talk about I²C. It is a hardware communication protocol. It is how we can talk to multiple devices, usually sensors, with only 2 wires. There are 2 signals here. We have SCL, serial clock, and SDA, our data line, our serial data line. The serial clock is used to qualify signals on the data line and basically sync up with those signals and acquire them into the device. You have a controller here, and you have multiple I2C devices. Now, because we were only using 2 wires, we have to address the different devices. So the way that the communication protocol works is that you start with a start signal to alert all the devices, hey, a transaction's about to happen. Then you send out an address, a 7-bit address. When the devices see that their address has been emitted onto the bus, they will go, all right, I'm gonna get prepared to acknowledge this message. Next up, you have read and write. This is also transmitted by the controller. And this tells the device, hey, I wanna either read from you or I wanna write from you. And at that point, if the device is present on the bus, it will acknowledge the signal. And later on, depending on if you're reading or you're writing, if you're writing, the controller will write a byte to the bus, and the device will acknowledge it. Or if you're reading, the device will write to the bus, and then the controller will acknowledge the write operation. And if you find this kind of stuff interesting, there is the i2cbus.org that you can go to. It has all the information you need to know about how this protocol works. But the more important thing is that there are a couple of errors that are associated with I²C. There's the NAC on address, meaning that there's no device that's currently there. It would map to standard error code, no such device. And then there's also I/O error. Sometimes hardware can mess up, or maybe a device is talking on the bus that shouldn't be at the appropriate time. And this would be some sort of I/O error. Now, here's where things get a little tricky. That abstraction that I had was built so that not only could you use it for the pins on the microcontroller, but for anything that could represent an output pin, so that my students could write their drivers agnostic to whatever the implementation is, pass it along, and it just do the thing. So here we have some controller talking over I²C, and using that to control a couple of output pins that could be used for a variety of different things, LEDs, buttons, so on and so forth. And this is when I started to realize that all those other errors couldn't be passed out unless I use exceptions, which I'm not allowed to, or I change the return type. And I also considered, well, will my students ever need to return anything from an output pin? Well, I don't really know where they're gonna use that code. For example, they may use it for an LED that might not be very severe. Heating element, that could be severe. Emergency cutoff relay, that sounds very severe given the name. And you may recommend, well, maybe you should use something that's infallible, that cannot fail. Totally get you. But I don't know what my students' code is going to do. I don't know what any of my users' code is going to do. So I need to provide them information about if something went wrong. So I changed it. I used TL expected back in the day. I'm going to be using the term standard expected everywhere else. But for the most part, I made these little result and status variables. They basically just, for status, it just changes the T to be void, and then I have my error type there. And then whenever I wanted to return an actual value, I added another API here called driver level that can read it back out. I can add in the type here that I want. And this pretty much did the work. But I also considered what would my code look like from the user's perspective when they start to use it. Let's consider exceptions, the simplest example in my opinion. Blink LED, we turn on the LED, we wait a certain amount of time, we turn off the LED, and wait a certain amount of time. Makes sense? If we use standard expected, we have to check all of our return values. So get a status, check if it's erroneous. If so, return back unexpected, we're good to go. I will say, this is if we had the error propagator P2561. If we had this in the language, this entire talk would not exist, because this is a little too easy and I would have loved having this. If you haven't seen the syntax before, it's very similar and reminiscent to Rust's error propagator operator. except there's 2 question marks because we already have ternary for 1 question mark. But because I didn't have that, I had to go with the error propagator macro. Cool thing, GCC supports statement expressions. Oh, and the propagator macro here just does all that extra work of creating the if statements and then returning a value. But GCC allows you to return values from macros, which is really cool, not supported in MSVC, but that's the thing you can do. So now I have to consider which APIs need to actually return errors, and the problem is that almost all of them do. There's only a few ones, like interrupt-based ones, that should never actually return back errors, but all the other ones are basically fallible. For example, I had an interface for a generic motor. Well, here's a motor controller that's controlled over I²C. Here's a display that's controlled over I2C. I can't escape it. Almost everything can have I²C underneath it, and I don't need to explain all the other interfaces that could potentially emit errors because the foundation is that almost all of them could just be implemented with I²C and have those 2 errors be propagated. So I moved everything over to standard expected. And here's what I learned from my students. So for about 2.5 years of doing this, I asked my students, hey, how do you feel about this? I started off with the if-else statement, not giving them the macro at first. I was very allergic to macros at the time, and I still am. They hated it, despised it. They didn't use it. They just used the void cast trick to get over it, to just not have to check their errors. They knew what they wrote. Like, I'm not doing any error handling. My implementation never sends an error. I don't care. Once I gave them the macro, they did prefer to use it. They would use it, but they found it noisy and complicated. The students were also annoyed with the API-based error handling as it was viral, meaning that it continued to propagate through all their code. Almost everything had a return type of result or status, because it's kind of like async with JS functions. You cannot call a erroneous API without also having the ability to return it unless you handle all cases. And if they're building a utility, well, obviously, they may not know what to do to handle that error, so they need to propagate it up the stack. And it might be quite a far away before they actually get to code that they feel has the context necessary in order to actually handle it. And one other thing that students told me was that when they looked at the code for something complex, because they're building hardware code, so there's gonna be a lot of checks everywhere, they would have to mentally delete out all the macros in order to understand what the normal path of the code looks like. So every single semester, students will ask me, why not just use C++ exceptions? They're built into the language, why can't we use it? And here's the thing. I would go and say, well, here's the reason why you shouldn't use C++ exceptions. Bloats up your code, requires dynamic memory. We already talked about that in class and why that's a problem. And then I would show them articles, and I send them links, and I say, oh, I have all these resources that tell you exactly why you should not use them. And because they trusted me and they thought I was rather smart, I knew what I was talking about, they would go, cool, all right, well, that's all I needed. Some students would push me a little harder, and then I would give them more information, and then they'd be satisfied. But over time, something started to happen. I started to notice that, number one, I started to hate my own code. I hated having to look at my complicated code and trying to see through the macros. Even when I made the macros like a single letter, it still was annoying to see. And on top of this too, I had this realization. I don't know what I'm talking about. Yeah, I've read articles. I hope that they know what they're talking about, but I don't know what I'm talking about. I haven't tested it out myself. I know nothing about that black magic. So this got me on a journey to figuring out to, at the very least, see how to make exceptions work on my chip. Just to at least have a demo to show them, hey, here's why it's wrong and why you shouldn't use it. I tried my best. I couldn't figure it out. Maybe you can do better. So now I'm gonna go on a little journey to show you guys what I had to do to get exceptions to work on an ARM bare metal chip. Here's some of the code. We just throw no inline because the compiler is so smart. It'll just realize, oh, you're gonna throw, it's gonna terminate, or like it's gonna do this, it's gonna remove all the code. Here are a couple of the parts of the command. The only parts that are really of interest are exceptions, RTTI being enabled. This is just me setting the ABI and the instruction set that I'm using. And these are like 16-bit and 32-bit instructions. Here's the first barrier you're going to encounter when you attempt to do this. Exceptions are disabled by default for I think all embedded systems designed or created compilers and toolchains. So how do you fix that? Well, you gotta I forgot to include one other bit. Anytime you actually try to throw something, your code terminates. Anytime, no matter what. And it took me like, I think 3 weeks to figure out that it wasn't me doing something wrong. It was something with the actual like compiler itself. So the only reasonable thing to do is to recompile the toolchain. So you search for it, you download it, you extract it, you follow the PDF, and if you ever watch this talk, please add the PDF back. It was so straightforward and so nice to use, and your online web tutorials very confusing. You install your prerequisites, and you do one big step. You change their build script to no exceptions to exceptions. Configure it, make it, build it, and then you need to implement one other function. I know it uses dynamic memory, so I need to provide memory to it. There's a function called sbreak or setbreak or SBRK. You give it some memory that it can use to allocate, and when you try it out, it works. So after a couple of hours of tinkering with this, you can get it to work. But there's another barrier. Large binary sizes. Oh boy, look at this. All right, so here's our baseline, 2K. And above we have 150K. I just wanted to throw something and catch it somewhere. Why is it so much memory? It's 56 times bigger than using std expected, and it uses up 30% of my flash size. All to throw something? I don't know, that's a lot of features I could provide. Not sure if I want to do that. So, what did I do? I tried to find out where the bloat's coming from. I need to report back to my students what's happening. So, the only logical thing is to disassemble the binary, search through it to see what's happening, and eventually I started seeing some things. I'm like, what's standard string doing in here? I didn't use no strings. What's IOString doing in here? What's locale doing in here? I don't need to know my location in order to like convert currencies when I print them out. Like that's not necessary here. And then I start backtracing all the code until eventually it all points to terminate. That's weird. And then you look up the answer to this and you find the answer. Little drum roll. This is all you have to do. What you do is you omit the terminate handler. In this case, I just overwrite it. It's a weak symbol, meaning that if I implement my own version of it, it'll overtake the one the compiler provides you. And this changes our code size down by 91%. 13K is something I can deal with. I don't actually, at this point, I'm like, yeah, this is fine. 11 more kilobytes than I had before, that's acceptable. The question becomes why? Well, do you guys know what happens when you terminate on your computer? If you just do something and you terminate on your computer, what do you usually get when you throw an exception and it doesn't get caught? Core dump, yes, a core dump, as well as a message saying uncaught exception, name of exception, blah, 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 blah. Terminate is printing, and IO streams, it's a weird thing that only embedded people know. If you include it, not even use it, if you include it, you automatically incur a 120 kilobyte space cost because of how it does static initialization and all of that. So, if you eliminate that, you eliminate most of the bloat you get from exceptions. Great. All right, there's still some other issues. Dynamic memory allocation, I still have to deal with that. Well, I take a look at the throw in assembly, and I see, well, there's this thing called CXA allocate exception. I wonder if it's also a weak reference. Oh, it is, cool. So I can just implement my own. And the great thing is that since it doesn't use malloc, I don't interfere with any of my students who want to use dynamic memory allocation. I can provide my own allocation here. Don't worry about what's happening here. I'm gonna explain what's happening in here much later. And then there's one more. The specter of RTTI. My code's small now, because I don't have that many types, almost none of them. But as I begin to grow my program and create more user-defined types and create bigger abstractions, it'll become an issue and it'll start to grow. I wanted to eliminate that. I wanted my code size to be small. So we're gonna talk about how you disable RTTI for exceptions, or at least attempt to. So I replaced FRTTI with no RTTI. And remember, we need RTTI in order to operate correctly. So I ask you guys, and I'm gonna have you guys raise your hands, if you do this, the compiler either tells you you cannot use cplusplus exceptions with RTTI disabled. That's one option. The other thing the compiler can do is strip out all the RTTI information that's not involved in exception handling. Or number 3, the compiler is silent and removes RTTI information, and using C++, throwing anything becomes UB. Now, who thinks is number 1? Raise your hand. No one? Oh, we got one person. Okay. Who thinks it's number 2? A few people. All right, we got about 4 people. And who thinks it's number 3? Okay, question, are all of you guys Rust enthusiasts? Because the answer is number 2. Because The assumption that it's just going to do BUB is a bit interesting, but no, GCC just cleans it all out for you. It's like, well, we don't need all this stuff, so we're just going to only keep the things that you actually throw in the code. Everything else can be stripped out. So to me, and I'm going to skip over talking about the size of type info. I decided not to include that in this talk because it would take too much time, or not take too much time, but took extra time. I realized that I can control the memory allocation specifically for exceptions. So at that point, I was like, well, if I can control this and have some designs around this, I can get away, I can statically allocate the number of exception objects that I need to use in my code. When it comes to the whole standard lib, that's Terminate's fault. It had nothing to do with exceptions. And then RTTI, well, I'm okay with paying the price for the few types that I throw, but anything else, I don't have to worry about. There's still the issue of exception tables and algorithms. But before I go into that, we're gonna just talk about what I did next. I went into my code base, and I migrated everything over to exception handling. I wanted to see how my students would feel about it. And I don't actually have a slide for this, but basically my students loved it. They loved the experience not having to worry about all the macros and other things. At the same time, in parallel, I was also making another change to move everything over to result types, or not result type here, because I wasn't sure which one was gonna win out until something happened. There's a little area here saying I decided to transition to exception handling rather than return types. For large enough projects, exceptions are smaller in code size and faster when exceptions are not running or not being thrown. Here's what happened. I obviously had to refactor everything and test all my code, so I built a whole bunch of old projects. The small demos like blinker LED and like controlling a servo, those all grew in size, as expected, as it should. Then I went to my MP3 project that had like an SD card driver, a display driver, and a lot of other more complicated things, and I saw my code size get smaller compared to what it was before. And the thing is, maybe my code was not very efficient before with the result types, but the thing that hit me is that I never expected my code to ever be smaller with exceptions. And at that point, I needed to know why. Fast forward 3 years, I'm at CPBCon, and I decided to attend the C++ ISO meeting. Patrice Roy was doing a talk on the things happening in SG14. SG14 is a low latency group in the C++ committee. And he was talking about external buffers for vector, specifically PMR vector. I have used this for my embedded projects, but there's one key issue. Pushback doesn't report anything if you have any issues. And if you run out of memory, your allocator's just kind of sitting there. You could either terminate or you could throw. But I found that just having it terminate might be too harsh of a reaction. So I told him, yeah, when I spoke to him afterwards, it's like, hey, it's interesting. I would love to use this, but it can't because there's no way to get the information out. It's like, yeah, a lot of embedded people don't want to do that because there's no exceptions. It's like, yeah, it's a shame that embedded people don't use exceptions because then their code size would be smaller. And I explained to him everything I kind of explained before, and he's like, I'm sorry, what? Do you have data? And I was like, yeah, I have data. Unfortunately, I don't actually have the code that I wrote that I could show the difference of. That was in an old laptop, and that laptop's gone. But I said I can get you data, and I can present a small presentation. So here is a modified version of my hypothesis before I even started this. The thing is, in my head, I was like, all right, at some point, exceptions are heavier than result types, and after some point, it crosses. So my idea is that, well, there must be some cost for normal result types that looks like this. S of n is equal to a times n. A is your average cost per function call that needs to be checked, and n is the number of function calls that are checked. And then for exceptions, it is bm plus e, where b is the average cost of your exception metadata, m is your number of non-leaf functions, and e is the cost of the machinery, like lib unwind and such. And I asserted that a of n is greater than m. And there's one interesting little thing that you can think about, which is you obviously call more functions in your code than you have functions in your code, right? I think that makes sense. If almost all your functions are going to report an error, and you have 100 functions, you're not going to have exactly 100 function calls. You're probably going to have more than that, or at least equal to that. So here's my experiment. Generate a whole bunch of C++ code, and basically have such code that, defines classes, trivial, non-trivial, creates a sequence of function calls that call each other and call each other in a certain way. And then also with these functions, we'd create the objects, and then we call functions on those objects. I can't go into too much detail here, but I can at least tell you that the goal was to use stood expected and exception handling, to have two separate functions, or two separate files that are effectively exactly the same. The only difference is the error handling mechanism. And I wanted to focus on propagation because what I noticed is that in a lot of the code that I write, especially for embedded systems, the context on how to catch an error is usually higher up the stack, usually not at the lower level where the utilities are. So I focus more on the propagation versus the handling. Here are some experimental parameters. We're not going to spend too much time on this because we have other things we need to get into. And here's what some of the code kind of look like. Here is an example function. It might be a little hard to see, but there's function 11.8, function 11.8 up here too. We have this internal static variable, and that's this volatile static variable that's here to create a side effect so that the compiler doesn't just get rid of our functions. The compiler is very clever. And then we create an object, we call some functions on it, create another object, call some functions, blah, 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 blah. And then we take the result of this next function in the sequence and add it to another side effect global variable to ensure that the compiler doesn't try to get rid of those functions either. Same thing as over here, except now I'm just using expected. Here's what I got as my results. I was very excited when I saw this because it pretty much confirmed my hypothesis, at least to some extent. So we have two lines here. The blue line is exceptions. The red line is using result types. And the yellow line is a delta between these. The yellow line is the most important part. And one of the things that was really exciting was this number right up here, 8,067. That number is the size of the unwind, of the lib unwind, basically, in your implementation. I did a simple dump, calculated and summed up all the functions. Boom, it was around 8,000, maybe a little higher. And then this little number here kind of told me, oh, and I should probably explain, the y-axis is binary size, and the x-axis is number of checks. And negative 16 just tells you the cost of every single check you have inside your code, about 16.5 bytes per. Getting a little closer, you can see that the zero crossing is around about 580 checks, but this obviously changes depending on what you're doing in your code. There's a lot of things that can make this vary. I'm going to be frank, I didn't show you this to you to convince you. That wasn't meant to convince you. That was just simply to show you that something's there. In order to attempt to convince you, I'm going to go over how exceptions work from throw to catch, so you guys have a mental model for how all this stuff works. Things I'm not going to cover. Nested exceptions. Nah. Anything other than table-based exceptions. I personally believe that table-based exceptions are the best form of exceptions. I will not talk about supporting Java because you can support other languages with libunwind and C++ exceptions. If you didn't know that, your compiler will actually check to see if the exception being thrown is a Java object or not, and it'll use that to figure out how to propagate it. Just so you guys know, I made my own implementation of the exception unwinding, and I stripped that code out. I made sure I didn't include that feature because I don't care. I'm on a bare metal system. I'm only running C++. I don't need to worry about supporting Java. I'm also going to go over deprecated throw because no reason to. I'm going to talk about the three function categories. Understand that these are my terms. I don't think anyone else has talked about this before, but I see when it comes to exceptions, three types of functions. There are leaf functions. These are functions that don't call anything else. These functions have no exception metadata because no exception can ever go through them. They didn't call anything. They don't themselves throw either. And if you think, oh, well, what if I have a leaf function that throws? Well, as you guys saw, throw functions turn into a sequence of other function calls, so they're not leaf functions. Next up, we have trivial functions. Trivial functions are functions that call other functions, but don't need any cleanup, nor do they need any they don't have like a try-catch block inside of them. The unwinder knows, oh, when I hit one of these, all I need to do is unwind. So it just simply unwinds it unconditionally. And my personal observation, this might not be your guys' code, but at least for embedded systems, since we don't have string and other things like that, we use our AI. We use it a lot. We use destructors, but they're not as common. We'll use them for like locks for things, but in a lot of the cases, it doesn't happen as often. So most of our code is trivial functions. And then lastly, we have dynamic functions, which are things that can contain something that needs to be cleaned up, has a destructor, needs to be cleaned up as you unwind it, and also has a try-catch. To go further, we have to talk about the ARM calling convention and what the registers look like for ARM. So for ARM, we have R0 to R3. These are how you pass your variables. It's also how you return variables as well, or return data back from a function. If we cannot fit the inputs into R0 to R3, it'll fill up those first registers, and it'll push the rest onto the stack. When it comes to returning, we either return it in those registers, or if it's too big to fit in those registers, we tell the callee, allocate the memory for me and pass it through R0. In a way, ARM's ABI already required copy elision in a way, so that's a thing. R4 to R11 are the preserved registers, meaning that when a function is entered, it must save onto the stack the registers it's going to use. And when it exits, it's going to pop off those registers back onto their respective locations. R12 is supposed to be our scratch register. I have no idea what it's used for, so I'm not going to talk about it. R13 is the stack pointer. R11 is the link register. And the link register is an optimization that ARM decided after seeing x86. They're like, wait, for leaf functions, you don't need to waste time pushing things onto the stack. You could just simply put it into the register, which is a bit faster. And then the leaf function can just call branch from that register from LR to get back. And then you have the program counter, which tells you where you are in your program. Here's an example. Here we have a function called foo. We're going to push R4 and LR onto the stack. We're going to do a whole bunch of stuff. We're going to call some functions. Our return value is in R4, so we're going to move that into R0. Now we're going to pop R4 back into its location, and we're going to pop the link register back into PC. And that's how we return. So that's how that works. Next up, we're going to go over how throw works. Remember how we saw what the code turns into when you have a throw? We have some sort of allocation. We're passing the number 1 into R0, which is the variable that we pass into allocate. We want to allocate 1 byte. We have a couple of things that are happening here. And specifically, I'm actually going to just describe it here. You can tell that R0 is going to have, well, R0 should basically include and have a pointer to whatever's allocated on allocate exception. It returns a pointer. So use R0, it has that. R3 will basically have the type info for the thing that I'm throwing. And then R2, the second, hold on a sec. Sorry. It's moved into R3. R3 is moving to L1 or R1. This is the second parameter. The third parameter is the destructor call, which is why it's just passing 0, a null pointer. That's explained here. So when it comes to a throw, you allocate the thing, you construct it in place with that allocated pointer, and then you throw. And then you pass in the thrown object, the type info, and the destructor. But now that we know how the throw works, we can ask, well, what is allocate doing? Remember that weird code that I showed before? And I agree, maybe if someone's reading this, they're kind of looking at this right here, that terminate. It probably should be throw bad alloc, but I just decided just to terminate in this case. What's happening here is when you allocate your exception, you don't just allocate your exception. If you actually looked at malloc, you would see that the size is greater than the amount that you threw. The reason why is because we have this thing called the exception header. So it's attached to the back of the exception, and we throw the start of the thrown object. And then we just give a delta, so we return back the storage. Well, in this case, I have some static storage. I'm not returning back multiple exceptions. It's just one example, otherwise it'd be a little longer. And then I just add the exception header to it. Now, why do we do this? It's for ABI compatibility and flexibility. Now, GCC can continue to update their CX8 allocate, keep the ABI exactly the same, and not have any issues. So one of the things that we need this exception header for is for all of the state we need to hold. For example, you need to hold a virtual version of your CPU. You need to probably keep some sort of state to know what state you're in when you're unwinding. And you also can hold other cached information. The runtime can access all the fields in the exception header by just going in reverse of the backwards from the pointer that was passed. And now the exception header can grow and shrink as you discover things or as you add more features. And if you only called malloc directly at the call site where the throw was, and the exception header was, let's say, 100 bytes, and then later on GCC makes it 104 bytes, well, now you have an ABI break. What's in that header? Well, you got your ARM Cortex M CPU registers, you got your type info, you have your destructor, and you got your cache. The cache just includes like some state and some other information. Just note that this is not from libunwind. This is my own implementation. This is all you really need, but you can add other things if you want to do other fancier stuff. And then I have a record of all the other registers here. I put remove just because there's a chance that I can just remove this and optimize that away, reducing the overall amount of memory I need to allocate each one of my exceptions. Let's go over throw. Here's an implementation of throw. First things first, you're going to take your thrown exception, pass it into your active exception. This is a thread local stored variable, and this is used for standard current exception. Otherwise, you couldn't get current exception to work, although I do have a way to get beyond TLS with exceptions. We talk about that over beer. We take the thrown object, we extract out a pointer to or a reference to the exception header. We set the type info, we set the destructor, we capture the CPU state as it is there and add it to our write it to our CPU. We raise our exception, and if for any reason the exception unwind flow has a problem, it'll return and it'll terminate immediately. Next up, we got the index. I know there's a lot of information. Well, don't worry, it's not, actually it's gonna get worse actually. So we have the index. We've all heard about the tables that exceptions make. Here's how they're defined for the ARM ABI. This has nothing to do with x86 or the other architectures. Each entry in this table represents a particular function in your code. Each function that's a non-leaf function will get one of these entries. They are positioned relative to the appearance of the functions in your text section, meaning if the first function at address 0 is foo, and the next one after a bit of an offset is bar, and after that is baz, then entry 0, 1, and 2 will be foo, bar, and baz. And then you can just binary search to find what you need. Oh, and you use your program counter in order to go into the table in order to figure this out. Now, the actual entries contain a 32-bit address. It's actually a thing called a position relative 32-bit offset. I omitted talking about that because it's a bit weird. But basically, it's an offset from that location in the table out to where your code is somewhere else. And it's only 32 bits, even if you're using a 64-bit processor, like the ARM 64-bit processors. And here we have one of those offsets to where your data is, and likely it'll be in your exception table. There's a difference between the exception table and the exception index. No except kinda does this, but don't assume it does this actually. Actually, it almost never does this, and we're not gonna spend too much time, but if there is a function that must be just canceled out, just say, nope, stop and terminate here, this entry can become the number 1. If it's ever the number 1, then it just tells the runtime, yeah, cancel at this point. All right, here's another one of the items we have to go over, the unwind instructions. This is another area that people, may not have as much knowledge on. So the unwind instructions simulate the epilogue of the function except for the part where you return a variable. Remember, in your try block, if something threw, that entire scope is no longer valid. Therefore, you don't need to waste time returning variables up the stack. That's not a thing with exceptions. So all unwind instructions have to do is do basically 3 things. Subtract your stack, deallocate your variables, pop your registers back into their CPU, and then finally, if there's any other special weird like coprocessor stuff, do that weird coprocessor stuff. Fun little things, I think I have a little extra time. Did you know that ARM supports, in their runtime, the Intel MMX registers? Because at some point they used that in some of their original implementations for floating point, and then yeeted that out when they realized that it wasn't very good for them. The unwind instructions are 8-bit. I want to bring up one extra thing. ARM thumb instructions are 16-bit to 32-bit. Unwind instructions are only 8-bit, so they're a compressed version. Because why do you need more than 8 bits to unwind your frame? You're not a general purpose processor, you're just doing a single thing. And most functions only need 3 bytes of information to unwind them, because subtract, something represents subtract, and then pop. And then finally, at the bottom of the ARM ABI document, it tells you that they did some calculations and realized the maximal amount of instructions is 7 bytes per function. Here are all the instructions. It's not too bad. So if you see an opcode that has 0, 0, and then 6 bits afterwards, you take 0, 0, you take those extra bits, and you apply this equation to it, shift it over by 2, add 4, add that to your stack pointer. The other one here is meant for if your stack's going the opposite direction. Then you have pop. So if you see 1, 0, 1, 0, 0, the next 3 bits will tell you the range that you have to pop. Remember, the Kali reserved registers are R4 to R plus N, in this case. So you just pop from there to there. That's pretty much it. And that'll pretty much do the entire scope of all preserved variables. And if your stack is relatively large, we have this encoding that we use in order to, variable length encoding to gather up the data and then subtract away your stack. The last one I'll go over is finish, which is hex B0. And then we have refuse to unwind. If you do something as no except, but you still need to run destructors, rather than actually putting the can't unwind, it'll just throw this into your unwind instructions. Now we're going to talk about where these particular bytes are located relative to the exception table information. Before we get there, we have to talk about personality data. Why is it called personality? No clue. But the most significant bit tells you if the thing you're looking at is the personality information or if it's one of these. Remember how I said it was a 31-bit offset? Well, it's because that 32nd bit is used to tell you if it's actually an offset or not. The other bits are 30 to 28 are reserved. Personality index tells you what type of data structure you're dealing with. And then instructions are in 23 to 16, 15 to 8, 7 to 0. And this will be called the short personality with 16-bit scope. We'll talk about what the scopes are in a sec. Here we have the long personality with 16-bit scopes, another one with 32-bit scopes. You can see that the personality values changed to 1, and this one's over to 2. This one has a length to tell you how many words are remaining for your unwind. And then you have your instructions. If you have up to 7, then the last ones here become B0. You get padded. Everything is 4-byte aligned in the ARM ABI. Also, this is a bit silly. I think they expected that there was going to be more words, but in reality, it's only 1 to 2. So if they just removed that, it would have fit in 1 less word. Just saying, that could have been done, but we didn't save the space there, unfortunately. Fortunately, these are really rare to have 7 full instructions. All right, we're getting a little further. Now we have the descriptors. These specify when you are in a certain scope, when your program counter is within a certain range, do this. So we have an offset, and we have a length. And we have these little bits here, 0 and 0. Everything is 4-byte aligned, or actually 2-byte aligned when it comes to instructions in ARM, so the least significant bits are not useful. They decided to use these as flags to tell you what type of descriptor it is. If you see a 0 and a 0 at those bit positions, it's a cleanup descriptor. The offset tells you from the start of the function down where the program counter range starts. Then from there, add a certain length. That is your range. If your program counter is inside of that, jump to this location located at this thing called the landing pad. This will jump you to the spot in the function or in somewhere else in the code that knows how to destruct those objects. And the difference between 16 and 32 is 16 and 32 bits for the offset and length. So that's how you clean up your stuff in, with the ARM ABI. Here we have the catch descriptors. The catch descriptors use a 1 and a 0 at the 16 and 0-bit positions. They include the catch landing pad, and on top of that, they also include the type info pointer. Now, fun thing, I think people think that trying to compare type info is really complicated. No, they actually just, in GCC, you just compare the pointers. If they're the same, it's the same type. If it has some inheritance, usually there's another field called like parent. It's only 2 fields, name and usually just name. After that, if you have a parent, the other field is your parent. So you just go, are you it? No. Is your parent it? No. Then you're not it. And then the catch pad just tells you where to, it moves the pointer to the location of where the catch starts. That's what that offset does. Oh, and then the bit here on the left-hand side tells you if you're catched by reference, and the bit here tells you if you are catched by anything else is what they state. And then there's some other weirder ones, such as catch all, which are all ones for the type info address, or all like -1 for the catch all address. But this one's called catch all and terminate. I have never observed this in real code. I don't even know what this means, but it's in the ABI, so I wanted to show you this. And here's what a full descriptor would look like in the exception table. So we have an LU16 personality at the top, length of 1, because there's 1 extra word. We have the instructions here. We have 1 cleanup pad area. We have a catch pad that has a catch all. And at the very end, there's this little ... It's like maybe more descriptors here. At the very end, we have the end of descriptors, all zeros for 4 bytes to tell you that you hit the end. Now here's something that's really cool. If you write normal code, and you're also not using RAII or having destructible objects everywhere, and your stack isn't too large, you can get your code to be inlined into the index. So when This is the personality, the short personality information. Remember, most functions only need 3 bytes. Therefore, the exception table usually doesn't have a lot of your function's exception information. That's embedded directly into the exception index to save space. And now onto the exception table. Now this particular area is unordered, and usually it will only contain 2 things, really. It'll contain the LU 16 or 32 descriptors, because if it was 16, if it was a short 16-bit, a 4-byte descriptor, it would have been inlined. So if it's here, it's either a long descriptor, a long personality data, or it's this thing called the GCC LSDA. I have a lot of stories to talk about how I figured this one out. This one was, let's get into it. So here's the last data structure we have to talk about, and it is probably the one that is an absolute doozy. So what GCC realized is that that previous descriptor I told you about is not very space efficient. It takes up way too much memory that it doesn't need to. Maybe we could apply a compression algorithm on this data in order to make it smaller. So that's what they did. Remember how I talked about how we're not going to consider other languages? Well, they realized, well, if I'm going to support C++, I could just have my own language-specific data area for that specifically. So that's what they did. For all language-specific data areas, you start off with a thing called the personality function address. After that, you have, actually, before I start getting into it, let's move on to the next one. The next thing here, so we have the personality function address on the top. The next item is the personality data, the SU16 where all the instructions are, that's placed here. No different than what I've described before. And now I'm finally going to talk about what leb 128 is. I showed it in one of the unwind instructions. Now we're going to discuss it a bit. What it is a variable length encoding for integers. So if your integer is small, then it takes up a small amount of memory, and if it's big, it takes up more memory. We realized that most of those offsets and stuff for small functions aren't going to take up that much memory. They don't need whole 16 bits of resolution, so we can just reduce it down. The MSB for each byte in the sequence is a continuation bit. It tells you, hey, are there more bytes in the sequence? If it's a 0, that's the end of the sequence. And that's pretty much it. You take all the 7-bit parts, you OR them all together, and now you have your length value or your value for whatever. And if I ever use the term uleb, I'm just describing specifically unsigned leb 128. And if I say leb 128, I just mean signed. People sometimes use sleb, but whatever, I don't use it. All right, next part, the header. All right, so there are a couple of things in here. The first byte in the header is a flag telling you the format of the dwarf information. And because we're using embedded and we never keep that inside of our binaries, it's always just hex FF. So if you ever see hex FF, it means we've omitted the information. Continue on. Next up, we have the encoding for the type table. So here we have all these other sections here, the call site table, the action table, and the type table, and they have encodings. When I get to this part, pretty much there's only one encoding that ever gets used, so we don't have to worry about all the other ones. Next up, we have a uleb 128 encoded offset. This will tell us where, once we get past the header, where the end of our LSDA data is, so we can do all of our operations on it. Next up, we have the call site encoding, which tells us how the information in this area is encoded. And here, we have the length of the call site. This will tell us from here where the end is and how long this entry is. So if we ever hit that end, we know we're done. And what I found is that it's really common for this to only be 5 bytes in length. It could technically be bigger because these are uleb encoded values, but when we go further along, I'll describe why it's probably mostly just 5 bytes. Next up, we have the call site. The call site is very much like the descriptors from before. You have a start, a length, a landing pad, a location of where you need to jump location where you have to jump to relative to the start of the function when you've seen that, okay, this particular area is where we need to go. So same thing, are you within this range? If so, jump to this location. And the last bit here is the action record. The action record is a uleb 128 encoded value that jumps you from the end of the call site into some portion, some spot within the action table. And that's pretty much the call site. And there's a whole sequence of them until eventually you hit the end. The code for decoding this would look like something like this. You'd have some sort of cursor as you go through, and you would take the call site information, you'd use it to decode it, put it into start, length, you then check if they're in between, And if they are, you check if your landing pad is 0. If it's 0, it's the compiler telling you just simply unwind the function, don't go any further. Otherwise, we break out of this area and continue on to evaluating the next sections. I'm going to skip action table because you need to know the information about the type table before you can look at the action table. The type table has a list of all unique types caught in your function. And it's all unique, so there's no duplicates, meaning if you have two try-catch scopes and they both catch standard exception, then you only have one entry in this table. Oh, and everything is indexed negatively because we have the end of the site here, so they decided, just go negative. There's some reasons for that, but not important here. Oh, and if it's ever null pointer, it tells you just to jump directly into the code. This will make more sense once we go to the action table. Here we have the action table. The action table represents the order of all of your catch statements and cleanup regions in your code. Specifically, when you have like catch A, catch B, catch C, this will represent where if you're at A, if you're at B, if you're at C, and if you're D or basically need to clean up, it'll then have another entry for those cleanup scopes. In here, when we took that action record index, it'll shoot us some part in the middle of this. From here, we have this value called the type info or the type filter number, which is a leb 128 value. It's signed because if it's negative, it's for throws specifier. And if it's unsigned, it's for normal catch. And then we have another value here called the next record, which just tells you how far to move your pointer up before you reach your next value you should evaluate. And then you can see here that you can use your type info with the negative operator to get your current type info pointer. If the filter value is 0, it means that we're doing a catch-all or it's a cleanup. When the next record value of 0 has been reached, you know you're at the end. And if you ever get to the end and see that nothing works, like nothing has fit the type that you threw, you just unwind that function and continue propagating up. And if the runtime ever reaches a next value of 0, re-explaining what I just said. So once you find that, now that we're at this point, let's say you have looked at your type filter value, you've checked the type in the type info, and it all works. It's, oh, this is the exact type. We match the pointers, they work. What you do is you set R0 to your exception address, you set R1 to the filter number that we got before, you set the exception header address to that landing pad plus the function's address that you had before, plus 1 because that's the way that the ABI requires it. The LSB needs to be set to a 1. And then you install the rest of the registers into the CPU, which will jump you to the location in the code. And at this point, we have now reached the catch block. So here's a fun thing, and I think, I don't have a slide for this. Catch blocks turn into switch case statements in your code, in GCC at least, and Clang. That number we had for the filter number is associated with which catch we're supposed to jump into. So here, when we jump in, our landing pad is here, compare R1 with 1. And if it's 1, we have this little branch if equals. So we then jump over to this location. This is our catch. My catch just prints out a message. So we just go R0, fill it with the address of my pointer, printf, and that's about it. Before we get into the actual code, though, we have to call this particular function. It is called begin catch. And because R0 was set with the input parameter of a function, this function automatically has the input parameter set for itself. From here, it takes the pointer, it looks at the exception data, it says, hey, change the state to handled. This is how we know if we have, we need to know if we're handled if we ever throw again at some point and we realize the previous exception wasn't handled. That way we can terminate. And then what it does is it takes the pointer that you gave it and offsets it back to the thrown type so that the catch can use it. Now in this case, I never used the thrown type, but if I did, it'll just be using R0 to have all that information. Then you go to CXA end. This will then use active exception or standard current exception in order to take the exception information, destruct it if the destructor is not a null pointer, and then deallocate it. And now you're on the happy path. You're back. Let's say that for some reason, you had a value of 0, and I don't know why GCC does this, but for some reason, it like adds an end cleanup here. I think it might be like a pedantic or some sort of pedantic, or not pedantic, paranoid thought of like, if you accidentally get here with some other value, clean up. What cleanup does is whenever you do cleanup for any particular function, you will call the destructors, and after that, you'll call the cleanup function. The cleanup function just simply jumps you right back into the exception unwinding flow. It just calls raise exception. And that is pretty much what a catch does. Now to go into the flow for raise exception. Hope you guys have kind of been feeling the idea of this, but here's it kind of written out. Once you call raise exception, you locate the entry relative to your program counter. So you do a binary search, you find it. You check to see, hey, should we refuse to unwind? If so, set the exception to handled, call terminate. If false, check do we have any language-specific data. If so, evaluate the personality, see if the program counter is in that range. If not, and then we decide, hey, if we're in range, that means should we enter the function? If we should enter the function, we enter it. Enter the sad path, and if we see a cleanup, that means we've called some destructors, get right back into the flow. If we see CXA end catch, then we go back into the happy path. That's pretty much it. Now, let's say we don't have any data, like we have a trivially unwindable function. We see, oh, it just has personality, that's it. Cool, unwind it. And the unwinding flow is basically just you decode all of those different instructions, and you apply them to your virtual CPU. And keep doing this over and over again until eventually you get to the end, which main should have a refuse unwind, but that's also like implementation specific, but it should have a refuse unwind, and then you just call terminate at that point. And that's pretty much it, really. Extra notes would be GCC chooses between LSDA and the ARM ABI if one of them is smaller. And I've also noticed bugs in how it does unwind information. I need to submit a bug report at some point, or like a ticket, but I just haven't gotten to that point. So yeah, that's exceptions. So now that we've gone over exceptions, hopefully everyone's feeling okay after that bombardment of information. You guys can always watch the video again on YouTube if you want to, or email me if you have any questions, beyond this talk and this conference. But now I want to talk about the space size for all of these different data structures and the limits of their space. We're going to fill in all these entries here. Some assumptions. Number one, I assume your code is being compiled for the smallest size, just so that we kind of focus on small size, not like performance, because you can obviously, make things a little bit different that way. We're also going to make an assumption that all your functions are below 16 kilobytes in length. And I don't think I can press that link, but if you want me to show you the data later, I definitely can, or even after the talk. But I went to Firefox, I took the release build with debug symbols in it, I downloaded it, and I dumped all the symbols, threw them into a spreadsheet, and I asked a lot of different questions about how the actual code is. And from that, I asked, hey, how many functions are bigger than 16 kilobytes? 243. How many functions are in Firefox, at least for like the main binary? 354,000 functions. So not a lot of functions reach this, so I think that's a decent assumption, but maybe you guys have different use cases. And also, I'm going to assume that none of our functions have more than 63 catch blocks plus destructor paths. A destructor path is where, let's say you've created one object, you create another object, and they can both need to be destroyed at different times. Let's say the constructor for the second object throws. You need to still clean up the first object. So that is 2 unique destructor paths. There's also, every single time you have a catch block, there's another path you can jump into. 63 seems like a decent number, and actually, I'm using it for other extents, but I think people can agree that if you have 63 destructor paths and or catch blocks, that seems like a lot. And I'm also going to assume that all encodings are ULEB 128 because it makes things a lot easier. There are a lot of other encodings, but they're not super important. The exception index entry, 8 bytes, as defined by the ABI. Nothing too crazy here. SU16 personality data, 4 bytes, as defined by the ABI. Worst case for LU16 and 32, 12 bytes, as defined by the ABI. Cleanup descriptors, which are the only ones I'm going to reference because the other catch descriptor never gets used. So 8 bytes for cleanup, as defined by the ABI. Catch blocks. This one's interesting. Remember, they're switch case blocks, or they're switch case statements. So I actually disassembled this so that we can actually look at the assembly and look up how many bytes it uses up, and we can do some comparisons. So here, we have 2 bytes for the compare, 2901. We have 2 bytes for the branch of equals. And then we have 4 bytes for the end catch and 4 bytes for the, for the begin catch and 4 bytes for the branch and link to the end catch. The cleanup I'm not going to include because it's not exact. It doesn't need to be there. It could be optimized away, just saying. Or not optimized away. The compiler could change that to not include it ever again. So for all of these, about 10 bytes, because we need 4 and 4 bytes, 8 plus 2. Oh my goodness, that's supposed to be 12. That is my bad. So that might mess up a couple of things further along, but for the most part, we should get the point across. Then we also have the size of the action table. The next 3 items I'm going to go over are going to be a little more complicated because you have to do a little bit of math here. This one is simply all your cleanup scopes and catch blocks have their own entry in the action table, and each action table is only going to be 2 bytes. Why? Remember that restriction I put it for a maximum of 63 cleanup scopes and destructor paths? It's for this. If you only have that many, you can use a leb 128 value, which can be from -64 to 63. You can have that entire full range. Therefore, it can be represented as a single byte of leb 128. And the next record, all the records are placed locally close to each other. So they're almost never not -3 or -5 or something like that. So they're never going to exceed 63 as a value. So yeah, my assertion is that they're just 2 times A. For the type table, it's just 4 times the number of types that are unique because we have pointers and there are 4 bytes on our system. So 4 bytes here. For the call site, it is 4 times or 7 times, for the worst case, your number of scopes plus 1. Something that GCC does. I don't think they need to do this, so they could probably omit this, but that's a thing. Remember how we said that the limit is 16 kilobytes? Well, let's consider how, well, I chose that number on purpose. Start and length and landing pad, because they're all relative to the start of your function, because my function cannot exceed 16 kilobytes, can never exceed 2 to the 14 bytes, which is the maximum 2 uleb 128 values can represent. Therefore, you only need 2 bytes for that memory. And the action table can't exceed 2 times A, which is, in this case, 63. So it's 126, which is just a little bit shy from the maximum that uleb can support. Therefore, single byte. And then the extra scope is because GCC keeps a scope for when it starts the scopes at the first location where you call and has an additional scope afterwards. I'm not sure why, but it does that. And yeah, that's pretty much it from here. Now we have the LSD header. It is 5 bytes to 7 bytes. 5 bytes is the minimum, we showed that before. But what makes it grow? It can only really grow because it has these offset values here. Remember, the offsets are for the location at the end of the type table and the size of the call site. If my type table cannot exceed 63, then it's 4 times 63, 252 bytes. If the action table cannot exceed 63 catch statements and cleanup scopes, the size of it is going to be 126 bytes, meaning that we've only used up 372 bytes worth of our entire 16 kilobyte, sorry. For us to have any one of these offsets exceed 2 bytes to get to 3 bytes of uleb 128 value information, our actual data structure needs to somehow exceed 16 kilobytes in total. So we have 16,004 bytes left for the call site. That's the only area we haven't defined. We already know how big the table is, and we also know how big we don't know how big the call site is. Assuming the worst case of 7 times S or S plus 1, this would allow us to have 2,286 call sites, which won't happen because I also limited the number of call site destructor paths and catch blocks. So in general, no, your header's only going to be 5 to 7 bytes. So yeah, it's all well defined here. And that's pretty much it. The only thing that's wrong here is actually the catch block. I apologize. I don't think it'll change much though. Here's some examples. Let's look at it. So we have the trivially unwindable function. In this place, at this location, our only components we need for our metadata is 8 bytes because it's trivially unwindable. It's a trivial function, and it doesn't need anything more. It doesn't need a lot of stack size, so it's pretty much fine. If we added an object that could be destructed or a try catch, it would increase the size of this. Or if your stack exceeds 512, that's an ABI specific thing. If you exceed that, then you will almost always need at least 4 instructions. Here's a mutex, my little mutex. I call I write something to the bus. And from here, because we need an index entry, short unwind, because there's probably not much happening here. The short unwind personality 16. We're going to need a cleanup scope, which is another 8 bytes. And we're going to need an end of descriptor, which is another 4 bytes. Total, 24 bytes. And the size will not increase unless we increase our stack size, like I said before, which will add an additional 8 bytes. And the object destructor will add each object you add that adds another destructor will add another 8 bytes. If you ever add a try-catch, you'll start using the language-specific data area for GCC. If you have a try-catch, it gets a little more complicated. We're not going to spend too much time going over the math, but basically you can add all these bits up and eventually get 45. And the next slide here will tell you about what things will change and how it will grow depending on what you do. So if you add another catch, it'll cost about 16 bytes. Why? Well, actually it should be 18 because we just realized that the cost of every catch is actually 12. But humor me for now. We have 10 bytes, or in this case 10 bytes for each catch. Then we have a new type, let's say it's a unique type that we added. And then we need another action entry. So that's 10 plus 4 plus 2, 16. Well, 12 plus 4 plus 2, 18 really. If you add another try-catch somewhere else, you'll need another call site, so that adds another 4 bytes to your data. And then finally, if you add any other try-catches with duplicate types, just 16, because remember, we can reuse the entries inside the type table. Now, let's compare it to using return types as your error handling. So here's an example of calling 3 functions with either no error handling or exceptions. This is how much assembly that we get from this. All the other functions are going to do the same thing. They're just going to call 3 functions and add them together. So in this case, I'm using instead expected, uint32, and my error type is just an enumeration here. And we're doing the normal thing, get the thing, check it. If it's not, don't use it, add it to the sum, so on and so forth, blah, 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 blah. The amount of assembly for exceptions, amount of assembly when you set expected. So I'm not going to be concerned with all the return paths because return paths can get really weird in how they get formatted depending on which optimization level you're using. So we're just going to look at the cost of checking. Here it's 4 bytes to do the load and read byte, and another check to do the compare branch if 0. And then that'll jump you to B4, which is over here, which if you look at the end here, we have an addition to the stack pointer, deallocate your memory, and then you pop R4 and PC, pop registers back. This is a return path. There are actually 3 of them in here for some reason. I don't know why the compiler did that, but yeah. Cost is around 6 bytes per function call. Well, okay, that's first it expected. What about for bool? Must be much smaller, right? Kinda. It is less code. Usually, so this one's a really cool optimization that it did. It realized that it could use cbnz, which can only go forward a certain amount of length down into the code. So it's kind of limited, so it's not the most likely that it'll always be used. And everywhere else, for all the other function calls, it just compares R0 with 0, and if so, branch to F51E. And 51E is up here. Move false into R0, add to your stack, pop. 4 bytes. Rust, because they use result types for everything, so they must have some way to get around this, right? Not really. Same thing as instead expected. 6 bytes. But if you use uint64 or a very large return value, it gets a little weird. 4 bytes. So this changes depending on how large your error object is, but in general, Rust knows that for results, that R0 will have the information for the tag information. So it just uses that in order to figure out, hey, are you basically, are you 0? And if you are 0, branch to our return path. So 4 bytes. I'm just going to use 4 bytes for Rust and everything else. And now we get towards the end of all of this, which is talking about distributed versus centralized error handling. These are my own terms that I came up with. Distributed error handling is effectively just using or forcing your code to do error handling throughout the entire code base. You distribute the error handling throughout every single function. Every function needs to help and be in charge of taking an error and delivering it to the thing above them. And whenever you call some function like this that can emit an error, it'll either handle the error or propagate it up. There's ignore, but we don't talk about ignore. And yeah, this can be done. And also, all the other stuff, I didn't show like using like an out parameter, but it's the same thing. It's no different, really. Sometimes it's worse, but that's not super important. That's distributed error handling. Centralized error handling is like having a mail system. Rather than having every human being in your city know how to deliver stuff to every other person, you have a specific mechanism with the specific amount of resources allocated to deliver information from one location to another location. So you have one mechanism to do this for all your code. You pay for that mechanism only once. Where did I say that? Do I say that in this? I don't say that here. But effectively, exception handling is a form of centralized error handling. One central system handles propagating errors everywhere else with a little bit of additional metadata to make it happen. So here is my claim. I claim that centralized error handling schemes have an advantage in terms of code size compared to distributed handling. Here's why. Point number one, branches are not free. I don't know why we ever thought they were free, but they're not free. They never have been free. So if I wanted to add up these 5 functions and each one of them could emit an error, I know adding is a very simple thing, but I want to simplify it here. Well, the more checks I need to do, this all just simply scales. If your cost per check is 6, it scales a little faster. If it's 4, it scales a little faster. But for trivial functions, which I hypothesize or I claim are very common in most people's code, yeah, you just have the fixed size for the whole thing. You can call thousands, all the functions in your code, and it'll still be 8 bytes in total for your trivial functions that don't use up that much stack space. Here's a bit of a comparison. If I wanted to call 6 of these functions, I would have a compare branch, compare branch, compare branch for all of these while using exceptions, just the function address and the personality to unwind it. That's it. If I had something I needed to destruct, well, I got this here, and I add more entries, but it kind of compares the two between calls and this data structure here. This data structure will be fixed. If you try to call more functions, this will continue to grow. And yes, if you use a try catch, it's 45 bytes, actually 47, because I forgot about the 2 bytes for each catch. But that allots you about 11 to 12 functions. So if you're only calling a small number of functions in your code, sure, but I feel like there's something weird about having a strict limit on the number of functions you can call in your code in order to be smaller than exceptions. And here's my second point. This goes back to what I've been saying before. Most functions are trivially unwindable. Think about the types of functions that you write, and this helps more if you're an embedded, but if you are not an embedded, think about how many times you do need to use stitch string and need to put things together. Think about how often you're not just passing it in as a reference, which wouldn't cause you to need to destroy anything. Think about the types of functions that you normally read and you normally see and read. How many of your functions in your code base actually handle errors versus just propagating them up? And how much of your code actually has non-trivial destructors? Let's consider Audacity. Jason Turner, I was hitting him up and saying, hey, does these things make sense, blah, 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 blah. And he's like, oh yeah, you should look at Audacity to get an idea of what they do. So I looked at them. 1,054 cplusplus files that they have for Audacity. Out of those files, 39 actually have catch blocks. There are 60 triscopes, there are 69 catch blocks, and out of all their functions, only about 50 of them actually, the 177,000 functions, only 50 of them actually handle errors. Maybe because they think they're too scary to use, but the way that I see them using it, with some control flow incorporated, I feel like they were pretty liberal with their usage. And yeah, their exception tables only added around 0.8% to their overall code size relative to just their text section. I'm not including strings or anything like that, just their code. And it was like 15K total memory. So let's consider some code where 5% of the code actually catches stuff. This is way bigger than how much Audacity does, but let's just go overboard. 25% allocate objects and are non-trivial. A little more than half of your functions are trivially unwindable, and about 10% of them are leaf functions. Oh, and all C code is always leaf functions. Or I'm sorry, all C code are either trivial or leaf functions, so they just get trivial unwind. So for our try catch, remember we need 25, technically 27 bytes for all the exception info. Let's just use a larger average, 64. Let's say that our average cost for all of our cleanup functions, remember we need a minimum of 24 bytes, let's use 32. And then we have 550 trivial functions, which require 8 to 24 bytes. I'm just gonna use 8 just because it's actually rather not as common to have the other ones. I could have made it 10, but decided to just go with 8. If you don't like it, you can do the calculation again. It won't make much of a difference. We have 100 functions that are leafs. They cost 0 bytes. We add them all up. We get 15 kilobytes of data. Now let's compare that to how many checks we have in our code that were allotted. We have 3,900 checks in our code that if we called more than that, we would run out for our 1,000 functions that we're considering. That means that each one of those 1,000 functions has a limit of about 4 checked functions. So long as your code doesn't check more than 4 functions, then you're A-OK with this particular scheme. If you call any more, then you're paying extra cost for no reason. I didn't include the unwind mechanism. GCC is around 8 kilobytes, so that would have included 200 additional checks. Fantastic. Now we can have 6 checked function calls per function. Or if you use my implementation, which is around 2.5 kilobytes, I'm still trying to get it smaller. Don't worry, I'll get there. You'll have 4.5 function calls per function that you're allowed before you've gone too far. Here's kind of my conclusion. Why can C++ exceptions produce smaller binary sizes? Number 1, reduces code gen when calling fallible functions. You guys saw how big the code got once we moved over to using any type of return type for status. The unwind information scales with the number of functions you have, not the number of functions you call in your code. It eliminates the additional return paths. I didn't size them up, but a lot of them tend to be either a single instruction at the very least, or actually most return paths at least have, the additional code for additional code return paths can either be a single instruction, or it could be up to 3 instructions at a minimum, or 2 instructions at a minimum. But all that extra code gets added in as well. The cool thing is that because our unwind instructions don't need to do that much, they only have 3 purposes: subtract the stack and pop registers. They're a compressed representation of what would be a normal code. And you only pay for the propagation code once, the lib unwind and all of that. It does not scale with your application. And here's the crazy thing. I've already been saying it throughout the entire talk. It could be so much better. We haven't optimized exceptions. We haven't spent any time working on exceptions. I looked at the number of people who've worked on exceptions on GCC. Who has a number for that? Who has an idea? You don't say anything. I know I already told you. Someone? Anyone? Just yell it out. Go for it.
3?
It's not 3. For all of exceptions, I believe it's 32. And I think GCC has like 100,000 people who've worked on it. I think it's like something like that, or maybe it's 10,000. Maybe I got my digits wrong. For ARM, it's about 8. I hope to be number 9 at some point to fix up some things. Here's the first thing we can optimize. CXA and catch. Why do we need a catch for every single, why do we need a function call for every single catch block at the end? Just put one at the end and branch to it. There you go. Calls are 4 bytes. Branches are 2 bytes. We can do better with lib unwind. I've already made my version smaller because I don't want to include Java or other things that aren't necessary for my use case. So yeah, we can do better for size. We could add a 4th personality. Remember I said that length, we could get rid of that? If we did that, we can remove an entire possibility of having 4 words or 12 bytes of information for unwinding. And there's all this other encoding stuff. That's backwards compatibility stuff that they added into GCC so they can support all the different other ways that GCC used to encode the information in the call site. But it's version 0, and they never made a version 1. And actually, making more versions is actually pretty simple. I'm not saying by the compiler side, but like the actual implementation of the code for them is pretty simple. So we can make one that uses lib128 for everything, so we no longer need the encoding bytes. We also, if we had a version of GCC that didn't need any of that old stuff, you could potentially get rid of the entire version 0 in your code if you rebuilt it all, and not need the other encoding bytes or the decoding functions. You don't need the encoding bytes, and potentially, I've been thinking about it, the action table seems too long. Why do I need to know the next record? What if I just had a length after the action record in the call site table? Let's say it's 1 byte. Now I can just go jump me to a location, check, hit the length, cool. It's nothing, we have nothing to do here. Rather than having a next record that costs you additional bytes for each one of them. So there's a lot of things that we can do. Exceptions can be so much more than what we have given them now. So to be honest, I don't agree with any of these reasons to not use exceptions. But here's the thing. I haven't gone over time. I haven't gone over the performance side of this. I don't have time right now. I got like, what, 8 minutes left? So I think a lot of you guys have probably been thinking, but Khalil, what about the sad path performance? Okay, it's smaller, sure, but is it gonna take a week for my exception to get thrown? Well, look out for my next talk, cutting C++ exception time by plus 76%. I'm planning on, okay, so here's the thing. I know I can get it to like at least 85. I haven't optimized my code fully. I haven't actually optimized it. I just kind of implemented it. If you ever implement exceptions, you'll get a faster time than lib-unwind. If you read the code, I swear, you will immediately see what is this and why can't we just do better? Here's the expected, how much it takes to go up 6 frames. I'm not giving all the data because I'll show you later. Here's lib-unwind, 15,000 cycles. Oh, and I'm using this on an ARM chip who doesn't have any operating system or anything special like that. So I have a deterministic number of cycles. You'll always get the same number each time you run these algorithms or run these tests. And then my implementation, 3,660. So I am 6.5 times 6.5 times slower than just propagating up, but I'm at least not 27 times as slow. I'm trying to get this guy down to around 2, so it feels like, oh, just propagate up the stack twice. And also on top of this too, I realized I have full control over the code. I can add features. I can do more things. And actually, now that I've kind of started to see all the parts of exceptions, there are other things that we could potentially do. For example, if you ever want like a stack trace from your exception, I could extend the exception header to have a little block of memory where I can record all the functions that I saw as I unwound. Now we have a stack trace. Would you ever like better control over your exceptions? I wrote mine as single phase. I've also done a version for, well, I'm working on a version for 2 phase, but I realized I didn't care about the benefit you get from 2 phase, so I eliminated the other phase and got a speed up. Also, have you ever considered like, wow, when I use exceptions, I have no idea what could terminate my code. I have no idea if I add or change one of my libraries to, let's say, V2 or 1 point whatever, and it upgrades and changes the implementation, there's a new thing being thrown, and my code doesn't catch it anywhere. I would love to at least know, hey, these things will terminate your code unconditionally, if it ever happens. If your answer was yes to any of these, I have another talk that I plan to do later on after that talk, which is extensible C++ exceptions and exception tooling. Any questions? Yes.